So we continue with the gear design procedure, and this time we are going to talk about the helical gears. So at the beginning, we are going to have an introduction about the helical gears, and then we're going to go to the design procedure. So we remember that for the spur gears, the teeth were straight. Now for the helical gears, that the gears that have the teeth aligned at an angle with respect to the axis of the shaft. They are operate more smoothly than the spur gears of equal number of teeth. However, the additional axial forces or the thrust force is going to be generated during the transmission. And that's make them more effective, and they're going to have higher contact area, and thus the efficiency is going to be higher, and also they avoiding the noise generated at the high speed of the operation. So the helical gears is going to have a smooth and a quiet operation due to the gradual tooth engagement. So you remember that straight teeth in the spur gear, they're going to have a complete engagement every time. And that's what actually causes the noise at the high speed. The gradual engagement for the teeth is going to lead to a more smoother operation. The spur gears within the high speed due to the impact, the helical gears are good for the up to speed in excess of 5,000 feet per minute. They can withstand a largest capacity of up to 30,000 horsepower. More tooth engagement will allow for the greater power transmission for a given gear size. Parallel to perpendicular shaft engagement are possible. The disadvantages are more expensive because you can see that the manufacturing process is going to be more expensive. And this, the resulting axial thrust component also is going to be one of the disadvantages because this will affecting on the shaft and the shaft design and the shaft material property. So we remember that in the spur gear we have what we call the phi, which is the thrust angle. Now here we're going to have additional angle is going to be the helix angle. So the helix angle is typically in the range of the 15 degree to 45 degree. The circular pitch value is going to be equal to the pi d divided by the n as usual. The normal circular pitch value, or the Pn, is going to be equal to the p multiplied by the cosine of the helix angle. The diametral pitch value is n over d. Normal diameter pitch value is going to be the PD divided by the cosine of the helix angle, and the axial pitch value is going to be equal to the P divided by the tangent of the helix angle. So you can see now from this diagram, instead we're going to have the radial force, we're going to have the tangential force, we're going to have the axial force, and the normal force is going to be the sum of all. So the axial force here is going to be, well, actually, advantage and disadvantage at the same time. So we will go through the design procedure for the helical gears. Once again, we are going to go through the different equations, and then we're going to summarize that in step-by-step procedure that you can follow to solve the example for this topic. So let's discuss the forces applied in the helical gears. We have Wm, which is going to be the true normal force that acts perpendicular to the face of the tooth in the plane normal to the surface of that tooth. Okay, so what we mean by that, that's the face of the teeth, okay, and you can see that the normal plane is going to be this one, okay, so this normal plane, and the force, the Wm, is going to be perpendicular to the face of the tooth in that plane. So this is the normal plane, this is the normal force. So what you can see is that is going to be inclined by the normal pressure angle, the theta n, and that's what we call the helix angle. The helix angle is the angle between the two planes here, the normal plane and the force, we have the tangential force. Now we coming to the normal pressure angle is the phi n, the transverse pressure angle is the phi t, and the helix angle is the lambda given here. Sorry, epsilon given here. Now for the helical gears, the helix angle and one of the other two are going to be specified. The third angle can be computed from the equation tan 1. So you can see that tangent of phi n is going to be equal to tangent of the phi t, or transverse pressure angle, multiplied by the cosine of the helix angle. The tangential force, Wt, is that acts in the transverse plane and tangent to the pitch circle of the helical gears, and that causes the torque to be transmitted from the driver to the driven gears. Therefore, this force is often going to be called the transmitted force. If the torque being transmitted, T, and the size of the gear, D, are known, then we can calculate the tangential force. It's going to be equal to the torque divided by the diameter divided by 2, or the torque divided by the radius. So if the power being transmitted is going to be P and the rotational speed is N, which are known, the torque definitely is going to be equal to the P divided by the N. So we can summarize the power, torque, and the forces relation. The box to the left is going to be for the US units system, and the one to the right is going to be the power, torque, and the forces for the SI metric unit system. So for the US unit system, or the IP system, we bring the concept of and the equations from the section 9 and 3 in the book developed for the spur gears and apply them for the helical gears. And these are going to be a unit specific equations. So when the power P is going to be expressed in the horsepower, the rotational speed is going to be in RPM, and the diameter D is going to be in inches. So the torque is going to be equal to 63,000 multiplied by the power in horsepower divided by the N in revolution per minute. And we're going to get the torque in pound-inch, or the force pound-inch. The pitch line speed, or the Vt, is going to be the pi d multiplied by the N divided by 12, and this will be in feet per minute. And the tangential force Wt is going to be 126,000 multiplied by the power divided by the RPM multiplied by the diameter. And finally, the Wt can be also found directly by multiplying the 33,000 multiplied by the power divided by the Vt, because we just simply replace the equation for the Vt instead of the pi dn divided by 12 in this equation, and we're going to get a new factor for the multiplication. Now we're going to the SI unit, which is mainly what we are going to use most of the time. We are going to bring in the concept from the equation of the section 9.3 and section 9.10 developed for the spur gear, and we apply them for the helical gears, and these are going to be a unit specific equations. So when the power is going to be expressed in kilowatt, rotational speed is going to be in RPM, and the diameter are going to be in millimeter this time. So the torque is going to be equal to 9,549 multiplied by kilowatt divided by the RPM. For the pitch line speed, is going to be the pi dn divided by 60,000 meter per second. And the tangential force is going to be 19,099 multiplied by the power in kilowatt divided by the RPM multiplied by the diameter in millimeters. Or same way is going to be equal to 1,000 multiplied by the kilowatts divided by the Vt in meter per second. Now, after finding the tangential force and we found the normal force, we can use the transverse pressure angle, the phi t, to find the radial force. So Wr is the radial force that acts toward the center of the gear perpendicular to the pitch circle and to the tangential force. It tends to push the two gears apart. Wr is equal to Wt multiplied by the tangent of the phi t. Now, the Wx is the axial force that acts parallel to the axis of the gear and causes the thrust load that must be resisted by the bearings carrying the shaft. With the tangential force known, The axial force can be computed from the equation Wx is equal to Wt multiplied by the tangent of uh, the helix angle. You can simply try the example 10.1 and the 10.2 in the notebook as an exercise for finding the forces by using the equations that we listed here. So I found that this diagram is going to be very useful for you to list all the relations between the different forces. We can see here that we're calculating the value for the Wx, the calculation for the Wr, and also we can recalculate once again with having a different relation between Wt and the normal the normal plane angle and the tangential plane angle and the helix angle. So now we are ready to go for the next stage, which is going to be the design procedure. Before that, we are going to continue to find the parameters required to do the design procedure, which mainly going to be about finding the stresses to be exerted on that gear. So the helical gear design, mainly everything for the helical gear design is essentially going to be the same as what we have for the spur gear. The fundamental difference is going to be using the J and the I factors. The bending stress in the helical gear teeth is going to have a similar equation to the one we had earlier. So it's going to be Wt multiplied by the Pd divided by the Fj. You remember it was I earlier, multiplied by the factors, parameters Ko, Ks, Km, Kb, and Kv. The overload, the size, the material, and other stuff. So the Ko is the overload factors for the bending stress. The Ks is going to be the size factor for the bending stress from table 9.2. The Km is the load distribution factor for the bending strength. And the Kb is going to be the rim thickness factor. And the Kv is going to be dynamic factor for the bending strength. And the J is going to be the geometry factor. And this can be found from the figure 10.5 and the 10.7 we are going to present to you soon. So we start with the figure 10.5, where we're going to find the geometry factor for the 15-degree normal pressure angle. So we can see that for the geometry factor J for the 15 normal pressure angle and the indicated addendum, you can see here that we are going to have the helix angle on the x-axis. On the vertical axis, the y-axis to the right, we can find the number of the teeth. So from them, if I get to know what the helix angle and the number of the teeth for the gear or the pinion, simply I can follow one of these curves and intersect it with the 15-degree, for example, helix angle, let's say with the 60 teeth, then I can simply find the value for the J, which is geometry factor to be 0.58. Now, here we're going to have the J factor multipliers, and we can find the modifying factors K. So again, we can see that the number of the teeth in the mating elements and the helix angle. Once again, to make the intersection, then we can find the value for the K factor or the modifying factor. So in case that we have the phi n or the normal pressure angle is equal to 20 degree, we can use the figure 10.6 and using the same procedure to locate the value for the geometry factor J and for the modifying factor K. Again, for the pitting resistance, we need to find the I value, which is the geometry factor for pitting resistance. So the equation for the contact stress number or the SC number is using the same equation that we learned earlier with a quite difference. Like you can see that we have the FDP at the denominator, we have the WT, KO, KS, KM, KV, and everything to be going to the power of 0.5 multiplied by the CP. So it's going to be the other terms that has been usually notation defined in for the spur gears. And the I now is going to be the geometry factor for the pitting resistance that we can get it from the graphs. So the geometry factor for the pitting resistance I for the helical gears with the 20-degree normal pressure angle and the standard addendum are going to be listed in the table 10.1, while for the helical gears with the 25-degree normal pressure angle and the standard addendum are going to be listed in the table 10.2. So this is table 10.1. That's for the helix angle of 15 degree, and this for the helix angle of 25 degree. And here we can see that we have the phi n is 20 degree. So 25 is going to be table 10.1. So again, what we have here is the gear teeth and the pinion teeth, and we can do the matching. So if 17 and 17 is going to be 0.124, this is better to have the same teeth number for both. For example, I'm going to take the 35 against 17. I can get the 26 against 26, 26 against 21, the 26 against 17. For the 135, can match with the 17, 21, 26, 35, and 55. So this is the value I'm going to get for the I. We're going to use it in the equation that we saw in the previous page. Now, let's jump to the next. And in this page, we are going to find the table 10.2, which is going to be geometry vector for the pitting resistance I for the helical gear with the phi n equal to 25 degree. And once again, that's for the helix angle of 15, and this for the helix angle of 25 degree. So again, the steps of the helical gear design has been summarized to you as the steps. The step number 1 is going to be to specify the normal diametral pitch, the pinion teeth number, the helix angle, and the normal pressure angle. We need to compute the values for the transverse diametral pitch value, the axial pitch, the transverse pressure angle, and the pitch diameter. Then we are going to choose the face width. We'll give the at least 2 axial pitch to ensure that the true helical action is going to be achieved. And step number 4, compute the pitch line speed V and the transmitted load. Step number 5, compute the number of the teeth in the gear. Step number 6, determine the K values. Step number 7 is determine the bending stress, the contact stress, and the pitting resistance, and determine which is the governing stress, and select the appropriate materials to avoid the failure. So the helical gear design example we have is about a pair of helical gears for milling machine drive. It is going to be transmit 48.47 kilowatt or 65 horsepower with a pinion speed of 3,450 RPM and the gear speed of 1,100 RPM. The power is in form an electrical motor. We need to design the gears. So what we are given was the driver is going to be an electrical motor. The driven is going to be a milling machine. Now, of course, the type of the driver, the type of driven is going to help me to find the value for the KO, which is the overload factor. We have the power of 48.47 kilowatt. The pinion speed is given, the gear speed is given. Find the helical gear design based on this information. So the next is going to be the bevel gears.